Find the lightest I-beam. In this problem, a 14-foot-long I-beam is subjected to a compression load, P. The unfactored live load and dead load values are provided. The beam is connected with a fixed pin connection, and the maximum slenderness ratio of the beam is 200. Of the four possible I-beams, we want to choose the beam with the lightest linear weight, which will still satisfy the strength requirement and the slenderness requirement. We'll first look at the slenderness requirement, where the radius of gyration of the beam, r, must be at least the effective length of the beam divided by 200. The effective length equals the length, L, which is 14 feet, times the effective length factor, K, which equals 0.80 for a beam having a fixed pin connection. After converting the length to inches, the radius of gyration of the beam must be at least 0.672 inches. We'll return to this slenderness requirement later in the problem. But next, we'll look at the strength requirement, which states the sum of the product of the overload factor and loads shall not exceed the resistance factor times the nominal resistance of the steel member. We can also describe the left-hand side as the load demand and the right-hand side as the design strength. The load demand equals the largest load combination resulting from various load combination equations. The equations we need for dead load and live loads are shown here. After plugging in the given live load and dead load, the load demand for this problem equals 152,000 pounds. The design strength of the I-beam is a function of the critical stress, FCR, and the gross area, AG. After plugging in the given 0.85 resistance factor for a column, we can rewrite our strength requirement and isolate the critical stress, where the critical stress must be at least 1.788 times 10 to the 5 pounds divided by the gross area of the beam, AG. Now we'll return to our four possible beams and create a table where each beam has a row, and the columns will help us check the slenderness requirement and strength requirement. Since we're asked to find the lightest I-beam, we'll start with beam W8 by 18, and if this beam doesn't pass the requirements, we'll check the next lightest beam, W8 by 24, and so on until we find the beam which meets both requirements. For beam W8 by 18, the radius of gyration, r, equals 3.430 inches about the x-axis and 1.231 inches about the y-axis. Since we're checking for a minimum r value, we'll always use the smaller value, which will be the radius of gyration about the y-axis, ry. Since 1.231 inches is greater than 0.672 inches, the slenderness requirement for beam W8 by 18 is met. Next, we'll check the strength requirement for this I-beam. We can look up the gross area, which equals 5.26 inches squared. If we plug in this area into our strength requirement for AG, the critical stress for the beam must be at least 33,992 pounds per square inch. To compute the actual critical stress provided by the beam, we'll first need to compute the unitless variable lambda c. Because if lambda c is less than 1.5, we'll calculate the critical stress using the top equation. If lambda c is less than 1.5, we'll calculate the critical stress using this second equation. This threshold of 1.5 distinguishes the inelastic buckling range and the elastic buckling range. lambda c equals KL over R pi times root Fy over E. In this equation, we already determined the effective length factor, K, and the length, L. And the problem statement provides the yield stress, Fy, and the modulus of elasticity, E. If we simplify this equation, we find that lambda c is a function of the radius of gyration, r. If we plug in our value of 1.231 inches for r, we compute lambda c as 1.581. 1.581 is greater than 1.5, therefore we'll use the second equation to compute the critical stress, FCR. Plugging in the yield stress and lambda c, we find the critical stress in the beam equals 21,052 pounds per square inch, which turns out to be less than the minimum required critical stress. Therefore, beam W8 by 18 does not meet the strength requirement. Next, we'll evaluate the next lightest beam, W8 by 24. The radius of gyration about the y-axis is 1.607 inches, which means this I-beam also satisfies the slenderness requirement. The gross area of this beam equals 7.08 inches squared, which makes the minimum critical stress in the I-beam 25,254 pounds per square inch. Next, we'll calculate lambda c, which equals 1.9459 inches divided by 1.607 inches, or 1.211. Since lambda c is less than 1.5, we'll use the inelastic buckling equation to find the critical stress, FCR, which equals 32,477 pounds per square inch, which is greater than the minimum required value, and the strength requirement is met, which means beam W8 by 24 is the lightest beam which satisfies both requirements. When reviewing the possible solutions, the answer is B.